natural exponential function. To look at our natural exponential function, we're going to go ahead and look at our compound interest formula. We're going to look at a special situation in which you're going to invest $1 so that'll be P, at 100% interest, so R will be 1, and you'll be doing that for 1 year. And so we're wondering what's going to happen as we continue to compound this more and more. So we go ahead and plug in our 1, our 1, and our 1. And now we're going to look at compounding this annually. So that means n would be 1, and we get 2. Then what happens when we compound it quarterly? So n would be 4. Monthly, so n would be 5. Daily, so n is 365. Hourly, every minute, and then at the bottom, every second. So go ahead and use your calculator to work all those out. Now, as we are looking at this, you realize that you get 2 1/4, and I said that wrong, 2.44141. And yes, we're dealing with money, but for the sake of this problem, go ahead and carry it out as many decimal places as you can. We'll do the next one, and you'll notice as you compound more and more often, you're making more money. Daily, yes, we're still making money. We're not going up by as much each time. Then we go to hourly. Didn't really make a whole lot of money, but we made more. So in other words, we're making more. It's always increasing, but it's not going up by quite as much. So for every second, we get this here. And you have to go out several decimal places before you notice a change from when you were looking at the minutes. So is this right here, are all these numbers starting to level off at a particular value? Yes, they are. What are they all starting to level off at? Well, they're starting to level off at this. Well, that's referred to as our natural number E. What we were doing was just this limit thing and putting in larger and larger values. Well, since this number shows up so much in math, we give it a name. Instead of calling it pi like we do for the circumference of a circle to the diameter, we call it the natural number E. It's approximately what we figured out on the previous page. E is an irrational number just like pi, so we can't accurately represent it as a decimal. Shows up a lot in theoretical mathematics just like pi does. Now, if we were looking at y is equal to e to the x, we would say, well, this would have to be a growth graph then for this exponential function because e is greater than 1. Because remember, e was a 2.7 blah, blah, blah. And it's a growth graph whenever your base is greater than 1. Well, what is our y-intercept of e to the x? Well, you could actually plug in 0. E to the 0, well, anything to the 0 is 1. Do we have a horizontal asymptote just like our other exponential functions we looked at yesterday? They are all going to level out at a height of 0. So it's going to be y is equal to 0. What is your domain and your range? They're just like what they were yesterday. Your domain is all real numbers. Your range are all the positive numbers. You only get out positives. Well, here we have another formula. It's compounded continuously. P, once again, is still your initial amount you put in. R and T. R is your interest rate. T is your time. Remember to change R into a decimal. So if it's given to you as a percent, change it back into a decimal by moving your decimal point over. Here you're investing $100 at 12.5% interest for 10 years, compounded continuously. The key phrase here is compounded continuously. Whenever you see compounded continuously, you then want to use this formula up here. So compounded continuously is our key phrase to let you know to use this formula versus the other one. Well, looking at our problem, we know P is 100. R, change your interest rate to a decimal. And we know our time. We're then going to go ahead and just plug those into our formula. P is 100. E raised to the power of this. And then we're going to just type that into your calculator. Now, since we're dealing with money, we will round this to 2 decimal places. If you are trying to type this into your calculator, make sure you put your whole exponent here in parentheses. Well, here we're going to go ahead and basically do a reverse problem. We have our ending amount. We have our initial amount. We have our time, but we want to know our interest rate. Well, since we are dealing with compounded continuously, we know we're going to be using the last formula, which I often refer to as a Pert. A-P-E-R-T, a Pert. We know our initial amount, or our final amount, I mean. So we'll plug that in for A. We know our initial amount of 400. Our E, we don't know R, but T is 16. One of the ways to do this problem is to go ahead and put it in your y equals on your graphing calculator. You put the left side into y1, put the right side into y2. Then we need to adjust our window so it works in the context of the problem. Now, R is what we're putting in here for X. It's an interest rate. R can't be negative. An interest rate of 20% is really big. So I'm going to say let's look between 0 and 0.2. For my Y's, I know I'm starting out at 400, going up to 1890. So I'm going to go just on each side of that, go from 0 up to 900. When I look at the graph of that then, I get this. Then we could go ahead and have your calculator actually find where this crosses. You would want to go second, trace, down to intersect, hit enter about 4 times, and then it will give you your answer. That'll look like this. So basically it's about 5%. We can also work this out with logarithms, if you remember your logarithms from last year. Now, we want to try to get the part that has the exponent on it on one side by itself, which we did here. Now we're going to use logs. In this case, since we're dealing with the natural number e, we'll use the natural log on both sides. Your natural log undoes e. You now got to get rid of the 16, so you'd want to go ahead and multiply by 1/16. So then you get the decimal approximation to be close to 5. Now, if you don't remember the log stuff that we just did here, work it out with your calculator down here. We will be going ahead and reviewing all that log stuff later.